internal seminar for the AI divisions. And today we have fantastic speakers, two talks, one led by Keith Burkhart and the other one led by Fred Morstatter. So I'm going to introduce Keith first. Keith is a computer scientist at the Information Sciences Institute who specializes in understanding human behavior with physics-inspired models. He received his BS in physics and PhD in physics at the University of Maryland. And he'll be talking today about the benefits of hybridization from forecasting, he'll talk about humans are not robots, rules of sums, AI, and the pervasiveness of polarization. So his first talk was going to be about 20 minutes long. If you have any questions, please post them in the Q&A, and we'll spend a little bit of time at the end answering the questions about that talk. After the second talk, we'll have a short panel talking about how the two relates and the research that we do here at ISI. Keith?
Thank you, Deborah. Just an FYI, I'll make it a little less than 20 minutes to give more space for Fred. Today I'm going to be discussing sort of the idea of course, that humans are not robots. Basic idea is that humans have cognitive biases, and these biases get fed into the data that we train AI on. So it's good to sort of better understand what exactly are these biases. So AI needs human data, but are humans up to par, in other words? So data contains noise, but what really is noise in human data? In, say, statistics, we might think of noise as some sort of white noise due to, say, measurement error. But in reality, for humans, these mislabeled data or things of that nature can be due to humans having cognitive limitations or making legitimate mistakes based on their own sort of perception of things. So a wide variety of biases can affect decisions, such as popularity bias or bandwagon effect, the position of items or where items are seen on a screen, and say websites often take advantage of this. Anchoring, for example, if you see a low number, you start to think of low numbers, or if you see a high number, you start to think of high numbers. Primacy, the preference to see something you see first, etc. And what that can produce is garbage in and garbage out. So if you have bad data that's fed into your model can then create bad predictions. And this is seen, for example, in the need for fair AI, where if you have racist ideologies that are built into, say, text, and you're trying to train a language model on that, your language model will in turn be racist. It's not that the model is intrinsically racist, it's that the data is the problem. So in the presentations by myself and Ashwin, we're going to be discussing a few examples of human biases. I'm going to be discussing human biases in decisions, and then Ashwin's going to be discussing exploring opinions and how those opinions have effects on language, and in turn, how we can use language to predict someone's opinion. So the first paper I'm going to be discussing is called The Origins of Algorithmic Instabilities in Crowdsourced Rankings. And this is a paper by myself, Tad Hodge, Raisa de Souza, Christina Lerman, and Martin Postfai. The DOI is here, and I'm happy to share the slides afterwards. So the basic questions and background to understanding what this work was related to a paper, this famous Music Lab study by Sedgwick et al. In 2006. In this paper, they looked at ranking the best and worst songs by having a bunch of people rate these songs, and they had two experimental conditions. In the first one, they would give people they would randomly rank the songs that people would see, so that the first song someone could see could be a very good song, could be a very popular song, could be a very bad song, could be a very unpopular song, or any combination of therein. What they consistently found was that when these songs were randomly ranked, people were able to pretty accurately, collectively, that songs that were popular stayed popular, songs that were unpopular were consistently unpopular across, no matter how many times they repeated this experiment. Versus in the social influence condition, which is seen on the figures to your right, basically what they would find is that each time they repeated the experiment, there was an instability in the ranking. Some songs were very popular, some songs were very unpopular, and there's a wide array of times when songs could be unpopular and popular just by repeating this experiment again and again. But what you'll notice in the far right figures is that there seems to be a tendency for very popular songs to remain popular consistently, and unpopular songs to be unpopular, and it's really the songs in the center of this figure that have a very wide variance. And that's kind of like what that sort of question of why there's some stability and instability in these experiments are what we were trying to better understand. So our research questions were, how does quality and option appearance jointly impact decisions? When is algorithmic ranking unstable, as seen in the figures to your right? And how can we stabilize algorithmic ranking such that good answers are consistently seen at the top of a say a stack exchange board, or that items that would be of high quality can consistently be seen? So our methodology was three conditions. The first one was a guess condition where people would guess answers. Then we had two control conditions where you would have a question like the ratio of the larger or smaller shape in this figure, and you'd have two answers. In the control condition, the answers would be randomly ordered. In the social influence condition, the answers would still be randomly ordered, but one was called more popular, just at random. So we had about 600 subjects per condition, or 1,800 subjects in total, and 10 questions per subject. Our first finding was shown in this figure to the right. Basically, to understand this figure, note that we have this x-axis value A. When A is near 0, both answers that people see are equally high quality. They're equally close to the correct answer. And then as A gets further away from 0, the answers become more disparate. It becomes much more obvious what is the better answer, what is not. Basically, what we find here is we plot the human data, the experiment data, as those individual points. And the left figure is for the control condition, the right figure is for the social influence condition. And the line is a model we construct that is able to reconstruct what we see in the data with just two parameters. This data shows that basically there's a strong position effect with social influence, that people prefer the more popular answer. Even though this was somewhat controversial, there's been debate about to what degree does social influence actually affect decisions. And the other thing we notice is that as answers become more ambiguous, when it's less clear what is the better answer, the decision quality, the probability of getting the answer correct, gets lower and lower, to such a degree that if you have somewhat ambiguous answers, but you have this strong social influence condition, people more often than not will get the answer wrong if the better answer is on the bottom. So in other words, there's an objectively better answer in all conditions, but the more ambiguous an answer is, the more likely people are to get it wrong, and it follows this very particular curve. And we use this model to better understand ranking. The top left figure basically shows that under certain conditions, when the answers are very obviously different, or when you have low position bias or low social influence, the best answer is consistently ranked first when you go by ranking by popularity. So the typical idea used, for example, in stack exchange by default, or maybe more naive sort of ranking systems, you find that you do in fact get a correct and stable ranking only under the condition of sort of low social influence and when answers are very obviously different. But under most conditions, especially when you have strong social influence, you get an unstable ranking. Just by repeating the experiment, sometimes the answer is popular, sometimes the answer is unpopular. And that's in qualitative agreement with the Sajjan et al. Paper. And we can talk about this in more detail, but I know I'm short of time. Next thing I wanted to discuss was the simulations that we created and this algorithm we created based on the model. And basically what we find is that the figure on the left, or on the figure on the right, the black line is our algorithm which is able to infer what is the a true ranking of the items. And we find that we're consistently better than, say, popularity-based ranking, a naive model. And that even after many votes, popularity-based ranking is very unstable. The threshold between when popular ranking is stable and unstable passes a very particular critical point, shown in the gray line in the bottom right figure. So in short, we have an algorithm that can stabilize ranking and that can rank things correctly, and that there's a particular critical point, a sort of physics-like critical point, when the ranking goes from stable to unstable. Just as a brief conclusion, we model the relationship between quality and presentation, and that we have a model that sort of creates theoretical guarantees for the best ranking of answers. And overall, what this means for AI is that humans use heuristics, of course, and that these and this can affect human annotated data. We found that when answers were very obvious, about 10 or 20% of the answers were very random. People would make mistakes even when the answers were very obvious. And that in hard choices, maybe 50% or even fewer decisions were correct. So that tells you that there might be a need for dynamic numbers of human annotators to make sure that you're actually correctly labeling items, for example. So in the next presentation, we'll show how options correlate with social med and how they stabilize geographically. And why this is important to AI is that differences in opinion can affect language, and we can apply these differences to predict ideology. So for that, let me briefly introduce Ashwin. Ashwin is one of our students who's getting a PhD at USC. And in the limit of time, I think we'll just move on to the next presentation. So Ashwin, just tell me when you want me to change a slide.
Sure. Thanks, Keith. That was an interesting talk. So today I'll be talking about political partisanship and anti-science attitudes in online discussions about COVID-19. It's a paper in press at JMER, Journal of Medical Internet Research. It's a giant paper with Fred, Minda Hu, Emily Chen, Keith, Dr. Ferrara, and Dr. Lerman. Next slide, please, Keith. Thank you. So to understand what the paper is, I want to start off by explaining what polarization means. So polarization is basically the segregation of society into two or more ideological extremes. Several studies have done this work in the past, but most of them have been restricted to political partisanship or political polarization. We've had Michael Conover at the Indiana University, Pablo Barbera back then at New York University explored these political polarizations and come up with statistical models to predict partisanship of users on Twitter. But what we want to explore in this paper are the correlations, the ideological correlations that exist or coexist with political partisanship. And the recent pandemic sort of exposed us to that. We saw that there were a lot of anti-science comments going on, people who did not want to get the vaccine, people who did not believe that COVID was real, had a high correlation or a high partisanship flavor to it. And that is something that we explore in this paper. Keith, next slide, please. Thank you. So to do this, what we do is collect around 2.4 million users from the Twitter dataset. The Twitter dataset is publicly available. It was collected by Emily Chen, who is a co-author on the paper. And we geolocalize these users to the United States. So we have around about 2.4 million users, which is a small subsample of the dataset. And what we do is somewhat different from the other papers that I was talking about in the previous slide. Instead of using follow relationships or building statistical models, what we look at is the kind of links that they share, or more specifically, the pay level domains that they share. As we all know, media bias fact check is a prominent fact check source that allows us to have information about ideological polarizations of pay level domains. They categorize domains as whether they're pro-science, anti-science, left-wing, or right-wing. Oh, sorry. Okay. And we collect them and we segregate them into science, politics, and political moderacy. These are the three dimensions that we talk about. Oh, sorry. I think I lost the slides. Oh, sorry about that. Yeah, so sorry about that. Science, politics, and political moderacy. These are the three dimensions that we explore, uh, and and what we do is we map links into whether they're pro-science, anti-science by marking them as plus or minus one. Similarly for politics and political moderacy. Now, the thing that I want to explain about political moderacy is that it's the extent of political belief they have, how far off on the hardline or moderate scale they are. Uh, so using this, we average the pay level domains that they generate, and we generate something called as a domain score. Around about 0.7% of our 2.4 million users have a domain score. That's around 18,000 users. And these domain scores act as labels for the future inference that we're doing. So the inference, it's pretty simple. What we do is we collect tweets, we group them into user-specific documents. So we have users, we have all the tweets that they generate in a 6-month period from January to July of 2020. And each user's document is then embedded using fast text embeddings. The fast text embeddings were through a pre-trained model, publicly available through EPFML, that's EPFL's machine learning laboratory. And we train a simple logistic regression model to predict polarity across 3 dimensions: science, politics, and moderacy. And the table on the right side shows that the fast text model significantly outperforms our baseline models and the label propagation algorithm. The label propagation algorithm is what Michael Conover's paper discussed back in 2011. And our fast text embedding model consistently has significantly higher performance compared to the other methods. And then we move on to looking at the correlations of these polarizations. And if we look at the heat maps on your right, we do see that right-wing users tend to be more anti-science, with most of the density being concentrated over here at the bottom right corner. Uh, the left-wing or the liberal users tend to be more pro-science, right around here. Uh, and then another thing that we were exploring was the political moderacy, how hardline or how moderate they are. And we do see that pro-science users tend to be more moderate, whereas the anti-science users tend to be more hardline with their densities sort of uh, clustering right around here. And we move on to look at the temporal variation of how the number of these users or the fraction of these users grows or reduces over time. We break it down into weekly intervals from January to July. And we constantly see that there is a diminishing effect in play where anti-science, right, the purple bars sort of reduce, the fraction of these users reduce. Uh, oh, um, oh, okay. And pro-science moderates increase over time. This could be because of users entering or leaving, uh, which is what we saw on Twitter as well, with most of the anti-science folks just leaving Twitter and going on to other platforms like Parler and Gab, I believe. Thank you. Um, and then we move on to exploring the topics of conversation. These are basically the popular hashtags for each of the 6 polarized groups that we have. We do see the pro-science left trying to attack Trump, calling it the Trump virus, attacking Pence, calling it Pence pandemic. And this is sort of a validation for our method, and it shows us how well the classifier or how well our model performs in identifying these user groups, and these topics sort of confirm that. And then,
Ashwin, you have 1 minute, by the way.
oh, sure, thank you. This is my last slide. And we also look at the localization of polarized groups. Uh, I'm going to be very brief here. We see pro-science moderates mainly, and these are the fraction of states users being pro-science or anti-science. Uh, most of them are on the West Coast, DC, Vermont. Anti-science is mostly concentrated on the South, which is very much what we expect. Next slide, please. Thank you. So yeah, future work sort of, we want to look at friendship paradox and long-term dynamics, but this work gave us a model that can predict polarization in real time. And we also saw that polarization was multidimensional in nature, and there are correlations that can be explored. Thank you so much. Any questions?
Thank you. So please feel free to use the Q&A panel if you have questions. But I have one actually. When you, and this one's for Keith, when you ask people to choose the answer, do you actually ask them to tell you why they chose that particular answer as well?
Just a second. You can hear me, right?
Yeah.
Good. No, we don't ask them why they chose the answer, but that is a good point in the future. You know, we want to give them as simple a sort of task as possible to avoid people from quitting before they complete the experiment, because that can also create a sort of sampling bias where the people who respond are some sort of very dedicated group, and you won't get the responses of the typical people. But yes, that is a good point to look at in the future.
Thank you. So please feel free to keep using the Q&A panel. If you have questions for our presenters, there'll be more time at the end for questions. But let's move on to our second talk, which would be given by Fred in combination with Daniel Benjamin, Bahareh, Harandizadeh, and Yuzhong Huang. And his talk is going to be about the benefits of hybridization from forecasting to cultural modeling. So Fred is a research assistant professor of computer science at USC and a research lead at ISI. And his research focuses on understanding biases that occur in social data, cultural modeling, and developing hybridized AI systems. Fred?
All right, thank you so much, Deborah. So I'm delighted to be here and presenting with this excellent group. So what ties our group together is hybridization. And what hybridization is blending inputs from both humans and machines. So why do we want to do this? Well, it turns out that humans are really good at qualitative data. They can read blog posts, news articles, and kind of like synthesize these into beliefs, which we can then collect and use. Machines, on the other hand, are skilled at quantitative data, and lots of it. They can take millions, billions of data points and crunch those into statistics that are meaningful for a certain decision or prediction. And combining these two things can yield the best of both worlds. We've seen it time and time again in our research in different contexts, and we're going to share that to you today. So the themes of this talk, so the first is crowdsourcing. So combining inputs from multiple individuals often results in better performance. Aggregation, so not every input is really suited for each prediction task. And identifying the best inputs can really help improve performance. Yuzhong is going to tell you all about that here in a minute. We've also developed different mechanisms for hybridization. So we've developed ways to kind of inject machine knowledge into human systems. So things like the forecasting systems that we developed. And we've also come up with ways to inject human knowledge into machine systems. That's some of the cultural modeling stuff that Bahareh is going to present. So first, we're going to discuss forecasting systems. It turns out we built some of these here at ISI. One was called SAGE. So SAGE was a tool that would take human and machine input and would turn it into predictions, probabilities about the outcome of future events. Since then, we focused a lot on prediction markets. So prediction markets are platforms where people can buy and sell shares based upon their belief in the likelihood of a particular outcome. And we've been working to introduce models into these prediction markets. So in the context of forecasting systems, the first thing we're going to talk about is aggregation. And I'm going to turn it over to Yuzhong, who's going to discuss his aggregation algorithm. Take it away.
Yeah, so now I will talk about aggregation in a methodology perspective. Please go to the next page. Yeah, so to understand the need of aggregation, let's give a concrete example. So imagine we have a question, what will be the long-term interest rate for Hungary in July? Assume we are in January. So and we have 3 options to choose from. And we will ask the user to assign probabilities for all these options. this is a difficult problem, and we can take the crowdsourcing approach. That is, we can ask these questions to n users in our platform and get n individual forecasts. And depending on the need, it could be as few as 10 forecasters or as many as we want. Then we can, the result we collected will be laid out in the lower left table. And then now comes the need for aggregation. At this point, what's our best forecast we can make? How to better utilize and extra useful information from this large set of forecasts we received. There are several strategies. The most straightforward ones are take their average or take their median and maybe like remove several, obvious wrong answers. But a smarter one is we could look into forecasters' historical performance and only consider forecasts that usually give accurate forecasts in the past, likely they are experts, and then take the mean or median of their forecast. We could be even smarter, because this method assumes like each forecaster has a uniform performance on all types of questions, but actually questions could range from different questions could require different knowledge backgrounds, and some questions like this one are asking about the financial problems, and some could be political questions. And on the other side, each user will have a different expertise. It is not an optimal solution to ignore all these differences. So to address this, we need to model question similarity, added user similarity, and this is our deep learning method is really good at. So Fred, could we go back 2 pages? I think the slides come in arrow. Go yes. So these are our goals in developing this new aggregation method. We want our aggregation method is aware of the similarity between forecasting questions. This similarity is not manually labeled, like we label them as financial questions, social questions, political questions, but learned by our model. And we also want to have a measure similarity between users, a data-driven similarity. And this similarity, this will be both done by learning a useful embedding for both questions and user. And then with these 2 embeddings, we can assign aggregation weight per user question pair. So with that, each user could only work on the type of questions they are good at, rather than a single weight for a user and use this weight for all type of questions. Then naturally, there's an obvious solution. There's an obvious solution that can model it as sequence summary problems. There's an input, there's an output, and it is a well-defined problem and could be resolved by either recurrent neural network, self-attention, or a proposed method. We did some analysis. It is included in the paper as a takeaway message that the standard recurrent neural network or self-attention, its output is oversensitive to the last input and is not a good choice for the forecasting aggregation scenario, because the last input could be a random forecast. We won't allow the random forecast to destroy our aggregation results. So next page. So this is our primary contributions. We change from the self-attention to anchor attention. Actually, what's anchor here? So anchor is a vector of question embedding. It is a A, is the number, the letter A here. We only change in one place from the Q_I in self-attention to the letter A in self-attention. So in self-attention, we use the query vector QI, which comes from the last input to calculate attention score. But now we're using the question embedding to calculate attention score. So with this change, it will invariant to the order or the whatever user forecast, including the last forecast, it will not be dominated by it. And this A, a fixed query vector, reflects similarity between questions. So if we see a new questions, we know it is similar to an existing resolved questions and quickly find experts that are suitable for this type of questions. And although we can approximate this by manual labeling that assigns the forecaster into different groups. But this is a completely data-driven approach and could be learned in the deep learning methods. Another point is the alpha IJ, the attention score, now has a direct meaning, could be interpreted as a matching score between user and questions. And it could help in interpreting the model's decisions. Next page. So here are some experimental results. We performed our experiments in our developed Sage platform, and it's including 375 questions. So it's a relatively large data set, including more than 2,000 human forecasters paired with 18 machine models. So, and our evaluation metric is Bahareh score. It is in a 0 to 2 range, and the lower Bahareh score is means the quality of the forecast is better. So if we take the most simple approach, just take the unweighted average, we can see the mean Bahareh score is about 0.32. If we are smarter, like consider their past performance and take a weighted average, it is in a 0.3. And if using our anchor attention approach, the result will be 0.25. This is just an example showing how important the aggregation step is. They are working on the same set of individual forecasts with different aggregation strategy. The output could be very different. Next page. So this is an interesting result. Earlier, we mentioned that the anchor attention weight between the question embedding and the forecast could be interpreted as a matching score. Then we plot the relationship between this attention weight and the actual Bahareh score. We can see that there is a their correlation effect is minus 0.08 with a very small p-value, so means it is obviously existing such a relationship. So we can see better forecasts get higher attention score. So what does it mean? It means that for a user question pair, our model can, given whatever user question pair, our model can directly predict whether it is a good match. If it is a good match, then likely, the forecast produced by this pair will likely be more accurate. So it should be, so it means that the model learns to find good match, good candidates for, find the right user for given questions. So in this way, it helps extract the knowledge from the forecaster. Next page. And okay, some conclusions. So our proposed aggregation methods actually applies to all types of aggregation tasks because it learns similarity between questions from question text. So there's doesn't have any requirement on human labeling, and it also don't need any knowledge about the forecasting method. Everything comes from historical performance. And remember we are talking about hybrid forecastings, but so far there's no specific setup for either human or machine. They are treated evenly. So it actually works for human only ensemble, machine only ensemble, or human plus machine ensemble. And it will just learn from the historical performance. And it is extensible. So far we didn't do any feature engineering, but it doesn't require feature engineering, but it will be happy to accept manual craft features, like forecast expertise or the category of questions. And it also can be extended, like currently we are only talking about producing a single aggregation forecast. It can be also extended to like produce a daily aggregations along the forecasting period. So yes, this is a methodological review of our aggregation methods.
All right, and so now I'm going to shift to a different domain entirely. We're going to discuss how hybridization can be used to forecast elections. Next slide. And so historically, we've experienced some recent trends towards two predominant new methods. Historically, there was a single pollster who would make their own polls and make their own predictions. In the last couple of decades, we now have poll aggregators. And the title might be getting cut off. We have poll aggregators who collect various polls from whatever reputable sources they can access weight those polls and combine them with fundamentals such as local demographics. Next slide. And another even more recent trend are prediction markets. In a prediction market, you can think of as sort of a stock market for events where several individuals from the public place a bid or a bet on whether or not an event will occur. Right, so in this example, you would get 38 cents if Donald Trump had won, and you receive nothing if he doesn't. Right, next slide. And so these two methods have a number of different advantages and disadvantages. Right, models by their nature are backward looking. Their whole job is to find trends in historical data. They're very good at identifying valid predictors in a data set. But they tend to use a very limited set of variables in making their predictions, both based on data availability and to avoid things like overfitting. So overall, models are very well calibrated. That's the statistics of how they work, but they tend to be very sluggish to adjust to new information. Markets, on the other hand, are forward-looking. They're based on humans kind of projecting into the future. So they tend to be very flexible. They can respond to new information very rapidly, but that information can often be very arbitrary and is not necessarily well correlated with the outcome variable of interest. So overall, markets can adjust to new information very rapidly, but there's no promise of calibration. Next slide. So the environment we're looking at is the most recent presidential election. Specifically, we're going to look at battleground states. It's not that interesting to make easy predictions, so we're going to look at hard ones. And we're going to look at probabilities. So we're going to treat the daily closing price of the market, interpret that as a probability, as well as the daily model forecasts. Next slide. Right, so here you can see the predictions, and what you'll note in these two side-by-side graphs is they're not really doing identical things. You know, they could very well be spitting out the same outcome, but they're not. So for example, on the right, the markets are using a very truncated probability scale. So we don't see anything overall that's any predictions that are above 90% or below 20%. So we have people at either pole, and they tend to cancel each other out. On the other hand, models tend to seem to shift a bit more over time. So we see much steeper slopes. Next slide. So now that we've pointed out that these are very different sources, how can we assess their performance? So as Yuzhong was talking about, we can look at Breyer scores, which is squared error when you code the outcome as a 1 if it occurs and a 0 if it doesn't. The trick is, how do you aggregate it? So we're going to look at each day as a separate unit, and we're going to average across states. And when we do this, you can see in the graph that models do very poorly, far from the resolution date, and they do much better and better as we get to the resolution. Next slide. And so when we take the mean daily Breyer score across all these states and all these days, we get scores that look almost identical. So we lose the nuance that we've just pointed out, that there are these stark differences in how these two methods perform. Next slide. And so this brings us to this question: is can we take advantage of these various advantages of each system? So we start with something very simply, the most naive possible thing. Just take an unweighted average of the two sources, noting that the average can't beat a single component for a single prediction. And what we see is that we end up with a not a earth-shaking, but a substantial improvement over either single source. Next slide. But what we really want to do is something a bit more sophisticated, and there's a couple ways we could go about that. One is to take the market prices and input them similar to the polling inputs into a polling aggregator model, right? And we would weight those and dynamically over time. But what we want to advocate for today is inserting a model into a market. Next slide. And this is how this would work. So we would basically develop a trading bot, and the bot would always believe whatever the model believes. So in this case, it would believe the economist prediction model. We would then endow that bot with a budget
and certain risk preferences. And then we would give it the goal of maximizing the expected utility and specifically of its overall wealth across the entire outcomes. Next slide. Oh, go back one. And so basically what we're doing is we're taking a look at all possible combinations of outcomes, which in this these 13 states, it's about 8,000. And then we're carrying that out times the expected wealth, which is cash times withholding. And the other thing this allows us to do is test the value of integration. So instead of this absolute scale that we've been looking at in the Breyer score, we can look at a comparative evaluation. Next slide. And so this is what the profit that the bot makes looks like for individual states. And they tend to fall in these two categories. So on the left, you see Ohio, where it never really settles consistently on a profitable outcome. And that's about half the states. The other half we see on the right. Pennsylvania is the example, where it takes a little while to sort of adjust to a profitable setting, but then once it does, it increases in profit. Next slide. And so when we do this across all the battleground states, we end up with a 16% profit based on a $13,000 valuation. Next slide. And so to conclude, we've shown that models and markets do provide very different types of information and that their performance actually differs, particularly when we track it over time. So hybridizing does in fact succeed at boosting our predictive accuracy, but it also gives us a different way to think about performance. In other words, we can embed a model in a market and then track its profit, and that shows us a relative instead of an absolute outcome that we can assess or interpret more easily.
All right, thanks, Danny. So next we have Bahareh. So Bahareh is going to talk about something a little bit different, which is our work in cultural modeling. What we're doing here is we are building a system that can automatically learn the shared values of a particular culture. How this works is we start with the blue lines. So we learn from their text, their books, so on and so forth, a good starting point of these shared values. And then we refine them by asking them. So we're going to interact with members of the culture. We're going to give them surveys that are automatically generated. And based upon those surveys, we're going to refine our understanding, again, automatically. So we have lots of participants, and even though they don't know it, they exist in a hybrid system. So this machine generates questions to get a better understanding about the culture. They then answer it. And this continually refines our understanding of the culture or group. So I'm going to turn it over to Bahareh, who's going to talk about how we generate these questions and how we evaluate them.
Okay, thank you so much. Yes, the project that I'm going to talk about is a part of the things that Fred already showed you. So this is actually a question here is that how we can infer topic from the text using the prior knowledge of the experts. So this is a joint work with by me, Hunter from the UCLA, and Fred. So yeah. So here you can see that we have a bunch of like topics that infer from different models. I'm sure that you're all working with topic modeling, at least once with LDA topic modeling, and usually we are suffering from, and many models out there suffering from the coherent and diversity issues. So here I showed you that an example that, for example, in the right hand, we have so diverse topic, and also they are so coherent. So you can map each those circle to the specific topic, whereas in the left hand, we have some like noisy that you cannot understand that what is the topic is about and how we can map it. And also they are not diverse. So for example, we have two topics that are more or less talking about the election, or two topics that talking about the COVID issues. So how we can like having the better presentation of these topics in terms of diversity and coherent. Next slide. Then, okay, we all know that LDA is out there for a long time, more than 20 years now, but it suffers from two main issues. It cannot handle the large vocabularies, and also it doesn't utilize the semantic information in a word embedding. So last year, from the same group, Blake Group, University of Columbia, I guess, they presented another model, which called embedded topic modeling as an extension of the LDA that employs variational autoencoder to decrease the complexity of the model to inference the posterior easily, and also utilize the embedding information, which was substantially improve the result of LDA. Next slide. But still there's a problem with ETM that it cannot use the prior knowledge of the expert to infer the topic. And I will show you an example in the couple of slides later that how, for example, in a document that there is a topic that is dominant, like we use the COVID document, COVID corpus, and when the COVID is the dominant topic in this document, there is just when you see the results from the ETM, you see that many of those topics are related to the COVID because COVID is a dominant topic in this document. So how we can incorporate the prior knowledge of the expert to infer the topic that we are desired to infer. So how we can employ the benefits of the ETM and also expert to infer a topic that we are really interested to see the pattern in the corpus. Next slide. So here, because we don't have time, I don't have time to go to the detail of this model, but the blue boxes here just show the ETM, and the yellow boxes shows the component that we added in the keyword assistant ETM. So basically, we just regularize the parameters of this model to generate a topic that we are desired to see in the corpus. So if you're interested, I can talk to you offline about this model, but sorry, we don't have time for now. So yes, this is the data that I was talking about. This is actually a 1.5 million news article about the COVID. We just sub-selected some of the items from this data set, but if you go to the next slide, I will show, it shows that how the COVID information is so dominant in this data set. So but we are interested also to see that, okay, what was the situation of social issues during the COVID, like Black Lives Matter or business like change, or I don't know, financial information. How does those topics are changed during the COVID? So then I chose 5 topics, and then use these seed words that you see here. And still you see that the COVID information are so dominant in this data set. And then use these seed words to guide the topic modeling to infer the topics that I'm interested in. So yeah, here you'll see that KETM, the model that we proposed, are better in terms of coherency and diversity, and also the quality of these topics are much more better in a sense that it improve not only the ETM but other guided topic modeling out there. And this is the quantitative result, and we also, if you go to the next slide, we also have the qualitative result, that, as Fred said, we ask the people in an intrusion task to show them a high probable topic of one of the topics that we infer, and then we do the intrusion term from the other topic, that high probability word from the other topics, and then intrude them to this topic and see that if the people can say which word are not matched with the other words. And in this sense, also KDM shows the better performance compared to other topic modeling approach. Yeah, sorry, I couldn't talk about the model, but if you have any question, you can send me a message.
Right, thanks, Bahareh. All right, just quickly, land this plane. So conclusions: humans and algorithms make good teams. I think that's really what spans across all of this research. So I think the reason for this is because humans add breadth, they add nuance, they add this kind of qualitative perspective. But the reason they need machines is because the models actually provide an objective, data-driven center. I put the question after objective because we know that's not always the case, but that is the dream after all. Algorithms add structure to non-formalized human knowledge, another way of saying it. And also this works in many different settings, right? So we saw forecasting, prediction markets, topic modeling for human understanding. And it works at lots of different scales. So Danny was talking about prediction markets with people from all around the world forecasting. We also have this working in these very localized cultures. Yeah, so with that, I'll end the talk and we'll open up for questions.
Thank you. So if you're a attendee, please use the Q&A. If you were made a panelist, raise your hand or ask your question directly in the chat. Any questions? Pedro.
So a question for Danny. So Danny, now you have a way to make money in prediction markets. So did you make money?
I mean, this was a retrospective analysis. And so the it still sort of is an open question, and we are sort of applying for funding currently to test it, but of how this would actually play out in a real market. So all the adjustments that have to happen in real time could have some sort of unexpected behaviors. We are hypothesizing that basically what the model does is it gives a sort of more data-driven anchor. So even when someone has some very strong pre-existing beliefs, it should pull them back a little towards what the data is saying. So the goal is not for us to personally make money. The goal, I think, is to sort of stabilize the market so they don't jump all over the place so much. Now, there has been a debate. So there's someone else who looks at similar topics. There's a couple of researchers, and I'm forgetting one guy's name, but Andrew Gelman, who runs the economist model, is hesitant to ever participate in the prediction markets because of his sort of heightened status by running one of these models. Whereas the other approach is that the other view is that he should feel ethically obligated to participate in the prediction market. So in other words, that proves that he's making the best possible, least biased model that he can make.
Thanks, Danny. Just to add to that, I totally agree that he's ethically obliged to participate in prediction markets. And further, I would love to make money. We should talk offline. There's one really active prediction market called Polymarket that I really encourage everyone to check out. And they have a really active chat. And it turns out that the most productive forecasters use their own models. I guess the real bottleneck here is building models for a specific forecasting question. But I mean, as you well know, Pedro, but that's something that, I think is definitely worth pursuing.
Thank you. Any other questions? Okay, so what I ask the panelists to do, the presenters today, is to actually answer a question together. And the question is, how did cognitive biases affect your AI system methodology and all the various work that you presented to us today?
You want to go first?
I guess, sorry, Fred, you got a question.
All right, I'll go first. So there are two places where this showed up, two kind of cognitive biases. The first was we noticed in Sage that there was a strong reliance on the model. I even have a backup slide about this that I'll put on. And I'm going to present this slide and hand it over to Danny. Might want to have a psychologist chime in here. So the first is model reliance. So this chart here on the bottom is the distribution of people in the control treatment. These are people who didn't see the model, and people in the treatment condition who did. And you can see the first week, the model's around here. Sorry, the x-axis, right, is the percentage put on the right answer. So if you're at 1, that's where you want to be. You have all of your weight on the right answer. And if you're at 0, that's bad. And in this case, our model, it failed. It didn't do very well. And you can see over time, this model is adjusting itself and is actually getting worse. And the people in the treatment condition who can see that model are following it. So that's bad. We didn't want that. And this shows also that they're relying on this model as a source of information, which is kind of leading them astray. The second is confirmation bias. So this is kind of a cartoon of what this might look like. So imagine we have a human here. His prior is that there's a 60% chance that the event is going to happen, and he gets to see two models. One model says there's a 35% chance, and the other says that there's an 85% chance. They're both 25% away, and they probably should consider them sort of equally because they differ an equal amount. But time and time again, we see these humans relying on the model that actually agrees with them more, which is another problem that we have to worry about. Danny, is there anything you'd like to add?
Yeah, so I mean, we have a paper which this image is from that is looking at exactly this question. Fred and I with Andres and Aram, and basically what we find is that sort of all this stuff, the strategies, treating the model as if it's an advisor, trying to discern whether or not the model is going to be helpful on a given question, and these biases, so in this case, confirmation bias and anchoring on the model or model reliance, are all happening at the same time and they're all competing. So in other words, you really need to understand your setting. And in a setting like this, where it's highly uncertain and potentially highly complex, then you're going to get a stronger effect of biases, because the numbers themselves, I think, have less intuitive and absolute meaning to the individual. So they might feel that like, oh, this event might be a little more likely than this one, but I don't know how much more likely. I don't know how to assign a number. So whether conscious or not, I'm going to look at all these little clues along the way, what the other forecasters are saying, what the model is saying. And so I'm going to do some sort of calculation based on what I see in front of me. So I think the more uncertain you get, more complex you get, stronger effect you can expect from these biases.
Something I would say, from my perspective at least, in contrast to what was stated before, that as far as you were saying, Deborah, how cognitive biases affect your AI system, am I correct? So I would say, I think the biggest thing in our case was sort of studying that very specifically. So maybe I could actually show you some slides here, just a second. This is actually not from my original presentation, but from a similar presentation I created, where what we basically find is that there's a sort of a wide variety in guesses, and that this is sort of gives you the sense of noise, that while we're able to understand sort of people's typical behavior, people's guesses can be all over the place. And so these sort of cognitive biases, namely what people tend to I mean, for example, there might be issues with anchoring, et cetera, could push people to make certain decisions. So I think what our findings sort of contribute is the importance of understanding these biases when trying to generate sort of ground truth data. For example, I think our finding on the right is basically saying that if you're only listing one, if you're only listing one answer on top and another answer on the bottom, people are going to be having a strong preference for the top answer, or that and that the collective guesses of people, as shown here, can tend to be biased away from the ground truth or from the true answer. This means that if you're to take the sum of everyone's guesses and assume that that's ground truth, that might not necessarily be true. People's individual biases will add up such that the exact answer and what people collectively think will differ. So overall, I think this is just showing that the best thing to do is to understand these biases and then to attempt to mitigate them. For example, in this work that we started to create.
Thank you. And we're at the top of the hour, and I want to be respectful of everyone's time. So I would like to thank all of our speakers today. And if you have any questions, more questions, you know where to find them. Thank you, everyone.
Thank you.
Thank you.
Thanks.